independent events have a conditional version also. So first of all, recall events A1 and A2 are independent if the probability of A1, A2 equals probability of A1 times probability of A2. Then we're going to call A1 and A2 conditionally independent given B if the probability of A1 and A2 given B equals probability of A1 given B times probability of A2 given B. Now, neither one of these conditions implies the other, and let's look at some examples why. So first I claim that independence does not imply conditional independence. So to prove this, I just need one example of two events that are independent and then a third event B, so that the two events are not conditionally independent given V. So for example, let's toss a coin twice and let's define events H1 being the first toss is heads, H2 the second toss is heads, and E an even number of tosses are heads. Now our sample space is two heads, head, tails, tail, heads, tail, tail. So the probability of H1 is 2 out of 4, 1/2. And the probability of H2 is 1/2 also, 2 out of 4. Probability of H1, H2 is 1 out of 4. There's only one point in the sample space where we get heads and heads. And 1/4 equals probability of H1 times probability of H2. So that means that H1 and H2 are independent. All right, now let's look at probabilities given E. Probability of H1 given E is, okay, if there's an even number of tosses, then we can reduce the sample space and just look at H, H, and T, T. An even number of tosses are heads. So the probability of H1 given E is 1/2. And the probability of H2 given E is also 1/2. And the probability of H1 and H2 given E is also 1/2, which of course is not equal to 1/2 times 1/2. So this means that H1 and H2 are not conditionally independent. given E. So we have two events that are independent but not conditionally independent given this third event E. Now, unfortunately, conditional independence does not imply independence either. To prove this, I'm going to make some sort of artificial events using a Venn diagram. So the events A1, A2, and B defined by the Venn diagram So here's S with 4 elements in it, and let's make these 2 elements A2 and these 2 elements A1, and let's let B be the union of A1 and A2. So these events satisfy probability of A1 is 1/2, 2 out of 4. Probability of A2 is also 1/4. Sorry, 1/2, 2 out of 4. And the probability of A1 and A2 is 1/4, because this area here is 1/4, which is probability of A1 times probability of A2. So that means that they're independent. Oops, now that I look at my notes, it looks like I'm doing another example of events that are independent but not conditionally independent, which we did already. Alright, I'll finish this example and then I'll come up with another example which proves this claim. So here's another proof. Proof 2. So A1 and A2 are independent. And then if we look at them given B, the probability of A1 given B is 2/3, which is also the probability of A2 given B. 2 out of 3 in the union. And the probability of A1 and A2 given B is, here's A1, A2, is 1/3, which is not 2/3 times 2/3. Okay, now I figured this out. Now I claim for real that conditional independence does not imply independence. I'm going to use a similar Venn diagram. This whole thing is S. These 4 are B. These 3 are A2. And these 2 are A1. So this Venn diagram defines events. So this whole thing is S. Which satisfy probability of A1 given B. So from this circle with 4 elements is 1/2. And the probability of A2 given B is also these 2 elements out of 4. And the probability of A1 and A2 given B is, so this is the only element in A1, A2, is 1/4. Which equals 1/2 times 1/2. So that means A1 and A2 are conditionally independent given B. But the probability of A1 in the whole sample space S is 2 out of 9. Probability of A2 is 3 out of the 9. And probability of A1, A2, so again that's just 1 point, is 1 out of 9, which is not the same as 2/9 times 3/9. So that means that A1 and A2 are not independent. The end.